All right. So in the last class, we were discussing the basic concepts of complex functions. So we defined various sets, important sets, a closed circular disk, open circular disk, then neighborhood, the concept of neighborhood, then open annulus and closed annulus. We discussed these half planes. These were the sets, the way sets are defined, and complex plane. Then we discussed the definition of point set, open set, and connected set. So connected set is a very important concept in complex analysis. So if between 2 points, you can always join within by a line or a curve, all of which the points on the line or the curve, all of which belong to the set S. Then that particular set is called as a connected set. So we showed examples of connected set and not connected set. Then domain. Domain is an open connected set. That is how domain is defined. And complement of a set of points in the Argand's plane that does not belong to S. Then how did we define a boundary point? Boundary point is here. So this one was the boundary point. The boundary point is such that its neighborhood will contain points of S and will contain points of S complement. That is a boundary point. It will compulsorily, no matter how small a neighborhood you take. So that is a boundary point. Region is domain plus some or all of its boundary points. So that's how a region is defined. Now, a complex function, we discussed that W is equal to f of z. Z is a complex number x plus iy. And this function is u of x comma y plus I times v of x comma y. So u and v are functions of x and y. And we discussed what is called as, the z plane or the domain plane. Now, the mapping w equal to f of z, it maps to another plane, which is called as the w plane, or is the codomain plane or range plane, this Argand's plane. So as we discussed, a function cannot be discussed in it cannot be discussed the way we discussed real functions. It cannot be plotted on a 2D or a 3D scale, because the domain itself requires a plane to be defined, and the codomain also requires a plane to be defined. Okay, so the various ways functions are defined, we discussed this. Then limits, and we discussed the types of functions. Exponential function, important. E power z is e power x cos y plus I times e power x sin y, or e power x cos y plus I sin y. So this is a exponential function. Circular functions, sine function is defined as, in terms of exponential function, it is defined as e power iz minus e power minus iz upon 2i. That is sine function. Cosine function is e power iz plus e power minus iz upon 2, and tan is sin z by cos z, right? And then hyperbolic we discussed, and relationship between hyperbolic and sine functions in complex planes. So these are the things that we discussed in the last class. And finally, logarithmic function. All right. Now, before we move to the analytical, the differential calculus, I will want to do some problems on basics complex numbers and basic complex numbers and the basic complex functions. I will just share with you the set of questions that come in GATE. Just a second, I'll just share. Yeah, I'm sharing. Now, just to share with you, see, these are, I've classified around, this is around 20 years of questions from complex analysis in different categories: basic algebra of complex numbers, complex functions and mapping, differentiation, integration. Now, just to discuss with you, so algebra of complex numbers, you just see how many questions you get. Okay, from 1993 to 2013. You have got 14 questions. That means every year one question on simply the basics of complex numbers. Then let us look at complex functions and mappings. 9. Okay, and these are very simple questions. That's not very difficult. Then differentiation. 6. That means analytic functions, Cauchy-Riemann equations, what we will discuss. And then integration, very basic integral theorem to line integral is important, very important. You get so much on line integrals. And 14 as much as complex numbers, and then series, Lorentz series and residual. So basically complex integration is very important, and basic complex numbers is important. Okay. So I'll just do some problems from here. So now look at this part, basic complex numbers and complex functions. So practice problems. We will start. Okay, the first part, the real part of a complex number, Z, is very, very simple. Okay, so real part, how do we define the real part? Real part is X. Now Z conjugate is, so Z is X plus IY. Z conjugate is X minus IY. Now real part, if you add Z plus Z conjugate, you get 2X. So real part of Z, which is X, is Z plus Z bar by 2. So this is the solution. So this is the answer. This is a very simple answer, very straightforward. Now next. So 2 cos phi can be represented as, so this is functions as we discussed recently. All right. Cos phi can be represented as e power I phi plus e power minus I phi by 2. Why? Because e power I phi will be cos phi plus I sin phi, and e power minus I phi will be cos phi minus I sin phi. So when you add this, you will get this one. This is the answer. Next. The complex number here, instead of I, J is given. So Z is X plus JY. Instead of iota, instead of I, J can be used as the unit imaginary number. So now complex number which satisfies this equation. Now mod of Z plus 1 is equal to 1. We know that in the last class we discussed, distance between two complex numbers is given by mod of a minus b. So here, this we can write this as z minus of minus 1. Z minus of minus 1. Okay, this is equal to 1. So in the Argand's plane, what will this represent? This is real, this is imaginary. Now minus 1 is will lie on the real plane, and distance of z from this point minus 1 comma 0 is always constant equal to 1. So it is a circle. Circle of unit radius and center at minus 1 comma 0. Okay, the distance of z from minus 1 is always constant equal to 1. So that's the basic definition of a circle. So you can see these are very, very easy questions, very simple questions. It's not at all difficult. Just need to be careful. Very good. So all right, this one is on the properties of complex numbers. If there are two complex numbers, Z1 and Z2, what is true and what is not true? That's what we want to discuss. So let us take the first one. Each one we'll analyze. Okay, I'll do it here. Let's analyze this one. Z1 by Z2 is, okay, this is a typo error. This is a typo error. This should be as far as now, it should be this. There's a typo error here. I will just check this. So let us look at the left hand side, Z1 into Z2. Now Z into Z bar is mod Z square, correct? Because x plus iy times x minus iy gives us x square plus y square, okay, plus I square y square. So I square x square minus I square y square, and minus I square is 1. So that's how you get this. And this is nothing but modulus of z the whole square. Modulus of z is under root of x square plus y square. So what we get, you can see here. So 1 mod z, sorry, z bar over mod z square is 1 over z. I bring the right hand side term to the denominator on the left, and this z to the denominator on the right. So what I get is 1 by z is z bar by mod z square. So I get this as z1 into z2 bar by mod z2 square. Okay, so this is z1 z2 bar by mod z2 square. This will be the first one. Second, z1 plus z2. is less than or equal to mod Z1 plus mod Z2. Is this true? Is this true according to complex numbers? Which is perfectly true, because complex numbers, it follows the vector law of addition. Complex numbers always follow the vector law of addition. Because it has x plus iy term. So let's say this is z, z1, and let's say this is z2. Now, according to, complex addition follows vectors law of addition. So this one will be z1 plus z2, this point. So now let us look at this carefully. So this is the Argand's plane origin, point A, point B. Now distance of O to A is mod Z1. Distance from O to B is mod Z2. And because these are parallelograms, this will be mod Z1, this will be mod Z2. Now this one, the sum, this sum is modulus of Z1 plus Z2. Okay, so this is complex addition. Okay, so now mod Z1, mod Z2, and mod of Z1 plus Z2 are the sides of a triangle OA. Maybe you call this as C. So OAC triangle. So the sum of the two sides of a triangle is always greater than the third side. So this is the triangle inequality. Sum of two sides of a triangle is always greater than the third side. Equal to will happen only when they are collinear. If they are collinear, then this will become equal to. So this is a correct proposition. And then the same logic, the difference between two sides of a triangle will be actually lesser than the third side. In fact, the modulus of this difference. But here, what is given is the difference between the two sides of a triangle is greater than the third side. So this is a wrong statement, and we are asked which of them is not true. So therefore, this particular statement is not true. Why? Because, here sum of two sides of a triangle is greater than the third side. And here difference of two sides of a triangle is less than the third side. So these are properties of triangles basically. And then the last one we will see whether it is true or not. Mod of Z1 plus Z2 the whole square plus modulus of Z1 minus Z2 the whole square should be equal to this. Let us see that. Mod Z1 plus Z2 whole square is this. This can be written as Z1 plus Z2 times Z1 plus Z2 bar. Z1 minus Z2 times Z1 minus Z2 bar. This, by properties of complex numbers, this will be Z1 bar plus Z2 bar. This will be Z1 bar minus Z2 bar. Now, when we add, when we multiply, I get Z1 bar plus Z1 Z2 bar plus Z2 Z1 bar plus Z2 Z2 bar. Z1 bar minus Z1 Z2 bar minus Z2 Z1 bar plus Z2 Z2 bar. So what I get is that these terms get cancelled. Okay. So, and now this is mod Z1 square. This is mod Z2 square. This is mod Z1 square plus mod Z2 square. So you get twice of modulus of Z1 square, Z2 square. So this is also correct. This is a correct statement. This is a correct statement. This is actually this one. If it's a typo error here, so these are properties of complex numbers. Okay, this is a good question. The next one. Okay. Now consider the circle Z minus 5i is equal to 2 in the complex plane x comma y with Z is equal to x plus iy. The minimum distance from the origin to the circle. Minimum distance. So let us do, that's a geometry problem. Let us draw the figure. I'll draw the figure here. This is real. This is imaginary. So this basically is mod of Z minus of 5 plus 5i. So this is the center and the radius is 2. So center, this is origin 0, 0, and this is 5, 5, 5, 5, and the radius is 2. So this will be the circle. This point is 5, 5, center. And the radius is 2 units. Now, how to find the minimum distance will be you join the origin to the center. Okay. That distance minus the radius will be the minimum distance. This will be the least distance. Okay. So therefore, here minimum distance from origin to the circle is, I'll call this as center C. So is OC minus 2 units minus radius. Now OC is under root of 5 square plus 5 square. Distance between origin to 5 comma 5. 5 comma 5 is under root 5 square plus 5 square minus 2. So this is 5 root 2 minus 2. This is the answer. Okay. This was conceptually. If you understand the set, how the set of complex numbers is defined, based on that, we will easily be able to solve it. I'm purposely going through this, the whole set. Okay, the solution of a complex number. So where z is a complex number not equal to 0, then find the solution of z. So the solution of z, then z is a solution also of this one. Okay. So let us do this. So we get, z cube is equal to modulus of z. Not modulus of z. Z cube is z conjugate. So from this, what we get, two things we'll get. One is modulus of z should be 1. So this is mod z cube, and this modulus of z bar is same as mod z bar. So first thing is this modulus of z square should be 1. So mod z will be 1. That is acceptable. All the solution has this. Next, if that is the case, okay. If that is the case, z into z bar is mod z the whole square, which is equal to 1. So I get z bar as 1 over z. Okay. So now I write z cube is equal to z bar, which is 1 over z, since mod z bar is equal to 1, z bar is equal to 1. Okay. So now this gives, bring this z to the side, z power 4 equal to 1. So we have transformed this equation to this equation. So solution for this equation, z cube equal to z bar, is same as solution to this equation, z power 4 equal to 1. Okay. Somebody has a question. All right. Next. Hmm. Mhm. Now this is a what? It's not getting copied. Now this is an easy question, but it's a matter of how fast we can do it. So now 4 times you have to do. Um, if you keep multiplying this will you can get, but it will become difficult. This actually, if you remember cube roots of a complex number, cube roots of unity, this will be one of the cube roots transformed. Anyway, this is z is root 3 by 2 plus I times 1 by 2. Now, okay. Now, modulus of this, you can write it in the modulus argument form. Modulus of z is 3 by 4 plus 1 by 4 under root, it is 1. Argument of z, both are positive. So tan inverse y upon x here. In this particular case, remember argument is defined as the angle made by the line segment joining origin to the complex point with respect to the x-axis. So this is the argument. So argument of z is this. Tan inverse 1 by root 3, that is 30 degrees. Okay. So, or pi by 6. Now, so z can be written in modulus argument form as e power I pi by 6. E power I pi by 6. So z power 4 is e power I pi by 6 whole power 4, which is e power I into 4 pi by 6, which is 2 pi by 3. So this is cos 2 pi by 3 plus I sine 2 pi by 3. Now cos 120 is minus half and sine 120 is root 3 upon 2. So this is what we get. Okay. Another alternative to do this, if we remember, through complex cube roots of unity. Now cube roots of unity, there's a unit circle. You don't have to do all this drawing. It is just in the mind. See, cube roots of unity, if you remember, if z cube equal to 1, then 1 omega and omega square are cube roots. This is alternative, by the way. Cube roots of unity. Okay. So now 1 is 1 cube root. I will highlight here. Omega will be another cube root, which is at 120 degrees here. And another cube root at minus 120 degrees. Okay. They form equilateral triangle, 1 omega, omega square. So now what I do, and this omega is minus half plus root 3 upon 2i, and omega square is minus half minus root 3 upon 2i. These are cube roots of unity. Now, we have what is given to us is z is root 3 upon 2 plus I times half. Now, if I multiply this I with z, I times z, what I get, I square is minus 1, so I get minus half plus I root 3 by 2, which is nothing but omega. So I times z is omega, and what I want is z power 4. So what I do, I power z whole power 4 is omega power 4. I get I power 4 is 1 and z power 4. I write omega cube times omega. So z power 4 is omega. I power 4 is 1. Omega cube, because omega is the cube root of unity, omega cube will be 1. So this is 1 and this is 1. So z power 4 is omega, which is minus half plus I times root 3 by 2. So this is the answer. So an alternative method, using the cube roots of unity concept, we do. If you don't remember, just write as modulus argument form and we can solve this. Okay, in fact, directly you can write this as cos 30 plus I sine 30. So e power I 30 degrees power 4, and you will be able to do it. Okay. So one of the roots, acha. To do this, I'm purposely going through this in this class because I have not exclusively dealt with the properties of complex number theory. But there's so many questions that come on the basics. So I'm trying to solve these to recollect the basics. So we have to simplify this expression, minus 5 plus 10i by 3 plus 4i. What do we do? Multiply with the conjugate of the denominator. Both in the numerator and denominator, we multiply this conjugate. So now product on top, minus 5 into 3 is minus 15, minus 5 into minus 4 plus 20i plus 30i minus 40 I square upon A square minus B square. So you will get, 3 square plus 4 square. 3 square minus of 4 I square. I square will be minus 1. So 3 square plus 4 square. So 25. So now this one, I square is minus 1 here. I square is minus 1. So this becomes plus 40. Plus 40 minus 15 is 25. Plus 50I upon 25. So you get, dividing, you'll get 1 plus 2I. This is the correct answer. Okay, very, very basic. Okay, this is x cube. X is a complex number. X cube is equal to I. Here, I've written J, but we'll write it as I. Later on, we'll convert the I to J. Now, how to do this problem? We have to use, if you remember, we have to use De Moivre's theorem. Okay, which states that cos theta plus I sin theta whole power n, no matter what the number is. If it's a integer, it is different. If it's of the form p by q, okay, if it's of the form p by q, or I will write 1 upon q, then this will be cos 2k pi plus theta upon q plus I sin 2k pi plus theta upon q. Why you get this? Very simple. Because sin theta you can write as theta you can write as 2k pi plus theta plus I times sin 2k pi plus theta whole power 1 by q. According to De Moivre's theorem, you get this is cos n theta plus I sin n theta. Now because it is because this is a fraction, you will get multiple roots. That multiple roots you will get using this. Now k starts with 0, 1, 2 up to q minus 1. You will get all different roots. So this is what you will have to use here. So x cube is I is nothing but e power I pi by 2. E power I pi by 2 cos pi by 2 plus I sin pi by 2. Now x is cube root of this. Now I'll get e power I 2k pi plus pi by 2 whole power 1 by 3. So I'll get this, and k takes values 0, 1, 2. So put 0, I'll get e power I pi by 6, k equal to 0. This is for k equal to 0. Take k equal to 1, I'll get 2 pi plus pi by 2, that is 5 pi by 2 into 1 by 3. So I get 5 pi by 6. That is 30, 150. Then I put 2. So 4 pi plus pi by 2. It is 9 pi. 9 pi by 2 into 1 by 3. I'll get 3 pi by 2. Okay. So the answers are, this is cos 30 is root 3 by 2 plus I sine 30 1 by 2. Now cos 150 is minus root 3 by 2 plus I sine 150 is 1 by 2. Then cos 3 pi by 2 is 0 plus I sine 3 pi by 2 is minus 1. So these are the three roots. 3 cube roots of x cube equal to I. 3 roots of x cube equal to I. So of this root is given, this is not given, this is not given. So this is the answer. If minus I was there, that would have been the answer. Okay. When n is a positive integer or any integer, then cos theta plus I sine theta is cos n theta plus I sine n theta. Now, if it is a fraction, then whatever for the denominator, say 1 by q raised to 1 by q, you have to take 2k pi plus theta upon q plus instead of theta, and k varies from 0 to q minus 1. So these are basics of complex numbers. So next, this is a simple problem, product. We can directly do it. 10th one. 3 into 3, 9. Minus 8i square, that becomes 9 plus 8, 17. Straight away, you can mark this as the right answer. 17. And 12i minus 6i, so plus 6i. So you get this. Now, modulus of a complex number. It's not loading properly. Yeah. Modulus of a complex number in which there are ratios is See, mod of Z1 plus Z2 is mod Z1 over mod Z2. So the modulus of the first one is under root of 3 square plus 4 square, which is 5. This is under root of 1 square plus 2 square, which is root 5. So the answer is root 5. Okay, simple questions. Very, very simple questions. Okay. The next one on cube roots of unity. If complex number omega satisfies the equation omega cube equal to 1, that means it is a cube root of unity. Okay. So what is 1 plus omega plus 1 by omega, which is very simple. 1 plus omega plus omega cube by omega, because omega cube is 1. So I'll get 1 plus omega square. And sum of the roots of the complex cube roots of complex number is 0. Why? Because this is 1 plus omega is minus 1 by 2. The sum of all the 3 roots. I times root 3 by 2. Okay. Plus minus half minus I root 3 by 2. So you get 1 minus half into minus half is minus 1, and plus this I times 0, because these two cancel. So you get 0. Sum of the cubes, sum of the roots of the cube roots of unity. 1 plus omega square is 0. Okay. It was a very simple problem. It was oral actually, if you know the properties of cube roots of unity. Okay, I'll skip this 13th one, product. Oh, the product is simple. Okay, now next. What are the square roots of I? Square roots of minus I. So z square is equal to minus I. Minus I means, see, you should know how to write I and minus I. I on a unit circle, I is this point. It is, okay, imaginary unit on the imaginary plane, and this is minus I. So this is either, you can write this as 3 pi by 2, or we can write this as minus pi by 2. So I minus I can be written as e power I times minus pi by 2. This is in this form, polar form of complex number. This is cos of minus pi by 2 plus I sine minus pi by 2. So this is what it is. E power minus I pi by 2. Now z, so z square, I will write this as 2k pi plus pi by 2. So z is e power minus I 2k pi plus pi by 2 whole to the power 1 by 2. So you get this. Now k can take values 0 and 1 because it is square root. So when you take 0, when you take 0, e power minus I pi by 4. And when you take 1, it is 2 pi plus pi by 2, which is 5 pi by 2 times 1 by 2, that is 5 pi by 4. E power minus I 5 pi by 4. Now minus 5 pi by 4 is same as 3 pi by 4 because this is pi by 4, this is minus pi by 4, this is minus pi by 2, minus 3 pi by 4, minus 2 pi, and minus pi, and this is minus pi by 4 here. From this angle, it is 3 pi by 4. So minus 5 pi by 4 is same as, you add 2 pi to it, 3 pi by 4. These are the same angles. Okay. So you get e power minus pi by 4. So it is cos minus pi by 4 plus I sine minus pi by 4. And 5 pi by 4 minus 5 pi by 4 you can write as 3 pi by 4. So cos 3 pi by 4 plus I sine 3 pi by 4. So this is the answer. Again, we have used De Moivre's theorem or De Moivre's theorem. Okay, those were the basics. Next, complex functions and mapping. See, this one particular question has been repeated. Wait a second. How many times? 1, 2. Okay, 3 times it has been repeated. And that too in GATE 2012 in electronics, triple E, and industrial engineering, this was asked. And in 96, this was asked in mechanical engineering. Okay. I raised to the power I. Okay. What is this? I raised to the power I. How do we calculate this one? So I raised to the power I, we should know it is e power I pi by 2 raised to the power I power I. E power I pi by 2 is I. Raised to the power I. So you get e power I square times pi by 2, which is e power minus 1 times pi by 2. So e power minus pi by 2, e power minus pi by 2, e power minus pi. 3 times repeated. Simple question, but repeated thrice. E power z is periodic with a period of. Let us do this. Now e power z is a periodic function. Exponential, we did, right? This one, x plus iy. It is e power x into cos y plus I sin y. Now, so in the last class, we had done this. When you take yeah. Mm. See, this is e power x into cos. Fundamental period of cos is 2 pi, and fundamental period of sine is also 2 pi. So this is e power x, e power I times 2 pi plus y. This is e power x into e power iy into e power I 2 pi. So you get e power x plus iy 2 pi I. So this is e power z into e power 2 pi I, which is e power z plus 2 pi I. So f of z is e power z. Now f of z plus 2 power 2 pi I is also e power z times 1. Okay, because e power z plus 2 pi I is equal to e power z. So we get that this function is periodic with period 2 pi I. So this is an important question. Fundamentals of functions. This is an important question. Please note the solution. Hmm. So now this is talking about the transformation from z plane to W plane. So this is a function. W is f of z is z minus 1 by z plus 1. Now, there's all, what are the points, domain points on the z plane? Inside the unit circle, outside the unit circle, inside the unit circle, outside the unit circle. Okay. So on the z plane, there is unit circle. On the W plane, how does it reflect? So this is Z plane and this is W plane. Okay. So on the Z plane, you have unit circle. Okay. Now, how does it transform to W plane? So let us see that. First of all, let us simplify this and see how it looks. This is x plus iy. It becomes x minus 1 plus iy. And this is x plus 1 plus iy. So let us simplify this. X minus 1 plus iy by x plus 1 plus iy times x plus 1 minus iy x plus 1 minus iy. Here we get x square minus 1. Then so denominator is positive anyway. Numerator we will see, we get x square plus y square minus 1. Now minus iyx plus iyx cancels. Then I get plus 2i y x square plus y square plus 2x plus 1. Okay, I will write as x plus 1 whole square plus y. Now, let us look at this one. This is x square plus y square minus 1 by x plus 1 the whole square plus y square 2iy by x plus 1 the whole square times y square. Now, if point lies inside the circle, see, circle is x square plus y square equal to 1, this circle. Points inside the circle will be x square plus y square less than 1. So if it is inside, see, denominator is positive, the numerator will be negative. So this will be a negative quantity if point lies inside the circle. So on the W plane, you get a negative quantity. And what is the value of this negative quantity? Okay. This denominator is positive, numerator is negative. It can be ranging for different values. We need to find that. Okay, instead of, I'll try to simplify it another way instead of such a big way and see, we get a better result. This is z minus 1 by z plus 1, right? I will write this as z plus 1 minus 2. This is much better. I get this as 1 minus 2, which is 1 minus 2 into z plus 1 conjugate over modulus of z plus 1. So 1 minus 2 times. I get z conjugate is x minus iy plus 1. So 1 minus 2 is minus 2. Sorry, minus 2x. I'm getting minus 2x minus 1. Correct. Oh, this is only for this. One minus 2x plus 1. Same result. Okay, this is square, by the way. We get the same result. It's not a different result. This only is giving a better insight, not this one. Again, we'll have to simplify this and come to this only. So the first method itself is a better one. So this plots on the negative side, and y can be either positive or negative, so both. So some region here, it will be on the left half of the plane. So this maps the inside of the unit circle to the left half of the plane. This is right. This maps the outside of the unit circle to the left half of the plane. This is wrong. It maps inside of the unit circle to the right half of the plane. Wrong. Wrong. Outside of the unit circle Z to the right half of the plane. Outside of the unit circle means this term will be positive. This term will be positive. So this is also right actually. Because again, this will be plus and minus. If it's a multiple option question, then both are right. It will not be complete right half plane. Just a second. All right, the next question. A function of a complex variable W is log Z. Okay, where W is this and Z is equal to X plus Ij. And we know what log Z means. Okay, W is equal to log of Z. All right. Now, where U equal to constant lines get mapped in Z plane as. Okay. Now Z is equal to X plus Iy, which is R e power I theta. Now log Z is equal to log R plus. This is R e power I 2k pi plus theta. So I'll get log of I to 2k pi plus theta times log e. So log Z is half log R is x square plus y square plus I So now what he says is this is constant. This is a constant. This is log z. W is log z. This is u plus v, iv. So what is u? U is half log of x square plus y square. And v is 2k pi plus theta. Okay. Now, given that on w plane, this is a constant. This is a constant, let's say capital K. So we get x square plus y square is e power 2k. All right. E power 2k. Now, as k changes, this also changes. So these are concentric on the z plane. These are circles. As k varies, these are concentric circles. With center 0, 0. So let's go back to the options. So u equal to constant lines get mapped in the z plane as set of concentric circles. So this is the correct option. Okay. So just it is a play with complex numbers. Next, it's an important question. These two. The equation sin z is equal to 10 has how many solutions? Sin z equal to 10. Now what is sin z? E power iz minus e power minus iz upon 2i equal to 10. So we get e power iz minus e power minus iz is equal to 2i into 10. So we want what will be z. So e power, bring this to this side, squaring 2iz minus 1. This is 20. I into e power iz. So we get e power iz the whole square minus 20i e power iz minus 1 equal to 0. So you get e power iz, take this as a variable, minus b, 20i, plus or minus root of b square, 400 I square, that is minus 1, minus 4ab plus 4. A is 1, B is 4ac. So you get plus 4 by 2. So this is minus 396. So square root of 396. It's not a number. Factors of 396. So 99 into 4. So 9 into 11 into 4. So 36 into 11 is 396. So 6 root 11. So you get 20i plus or minus 6 root 11i by 2. So 10i plus or minus 3 root 11i. Okay. Now this, you will have it's a purely imaginary number. This one, it has two values, plus and minus. So you have 10 plus root 311i or 10 minus root 311 times I. Okay. So by default, you don't have to solve for the whole thing. This will be a complex number, e power x into e power iy. So cos term is 0, sine value into e power x. So you get basically e power x sine y as this. Of course, there are infinite values because this iy by definition, we know that these are periodic functions. So you'll get infinite values, which will be complex in nature. You won't have real solutions because already it is having complex terms. So sine z equal to 10 has infinite number of complex solutions. Okay, here the drawing object is not there. But anyway, I'll do this. This is an important question. Very important question. So a complex variable now z is given to be x plus I times 0.1. I have to find the locus of 1 by z in the complex plane. So 1 by z, so w is 1 by z. So it's transformation in the w plane. How does it look? 1 by x plus now x varies, x takes all real values. It's what it says. So you get x minus I times 0.1 upon under root of x square plus 0.1 the whole square. So we get x by under root of x square plus 0.1 the whole square minus 0.1 by under root of x square plus 0.1 the whole square times I. Now this for all real values, this will always be, the denominator will always be greater than the numerator. Okay, so this will vary from -1 to 1. It will not be exactly equal to -1. This will vary from -1 to 1. And simultaneously, this will also vary. It can take 1 when x equal to 0. It takes 1. So this also varies from -1 to 1. No, this will not, because this is always negative. -1 to 0. So on the x plane, the graph as x tends to 0, this varies from -1 to 1. As x tends to 0, it tends to 0. This is u. This is v. Okay, if we see the graph, let me just see if I can get the graph of this. Just give me 2 minutes. I'll check in another source. Okay, I got the question. I didn't get the exact question. Exact question is not there. There's a similar question. I will take that similar question. I'm just sharing the screen, just a minute. Okay, this is the question. A point Z has been plotted in the complex plane as shown in the figure. It lies within the unit circle. Okay. Now, a similar question. So plot on the complex number Y equal to 1 by Z is what? So let's look at this one. Yeah. So this Y is 1 by Z. You will get X minus IY by X square plus Y square. Sorry, this is Y. Or I'll write W, doesn't. Now this is X by X square plus Y square minus X square plus Y square. Now, this is point Z on the unit circle. So given as X is greater than 0, Y is greater than 0, and both will be less than 1. Why? Because it is lying within the unit circle. So X square plus Y square will be less than 1. That is given. Now, where will this point lie? Firstly, because both are positive, so this term is positive and this term is positive. But this has a minus sign here. So remember that. So this is positive. Now, now will X square plus Y square be less than X or greater than X? X square plus Y square. Usually, because X lies between 0 and 1, X square will be less than X actually. Now, plus Y square depends on totally on Y, whether it is less than or greater than. Okay. So here it is showing some point slightly less than 1. So, okay. Now, this will lie in the positive quadrant and this will lie in the negative quadrant. So there are two options here. This is one option. Positive, no, x is in positive, the u is in positive, v is negative. So you have two possibilities. One is this possibility, other is this possibility. So now we have to see where does it lie? Does it lie inside or outside? So very simple now. Let us do this. Now mod z is less than 1. We'll do like this. W is 1 by z, which is z bar upon modulus of z whole square. Okay. Now modulus of this w is mod z bar by modulus of z bar square, that will be z bar. This is same as modulus of z. Mod z bar is same as modulus of z. So you'll get 1 by mod z. Now in the given question, mod z is less than 1. Therefore, 1 by mod z will be greater than 1. So of these two, this is the correct option. Of these two, this is the correct option. And if you actually take the modulus and see, you will get this: x square plus y square by x square plus y square, the whole square under root. So now x square plus y square is less than 1. So this will be greater than 1. That is the modulus. So a point here in the first quadrant will be plotted here outside the unit circle in the fourth quadrant by this transformation. Okay, so this is a conceptual question like this. So similarly, this one, I'm not getting figures. It is saying figures. I'll have to see. One of the books that I'm seeing, this figure is not there. That's why I shared a similar question. Now, the last problem for today. So modulus of e power I z. This is, I'll write this as e power I x plus y. So I get e power minus y times e power I x modulus. This is e power minus y times modulus of e power ix. Modulus of e power ix is cos x plus I sin x. Now modulus of this means root of cos square x plus sin square x. It is 1. So I get e power minus y. So this is the answer. All right, I'll stop here. I spent a lot of time on the basics so that the basic complex numbers can be understood, can be reviewed. All right, I'll stop here. Tomorrow's class, we'll do differentiation. It's a short term, and then we begin with integration also. Thank you. I end here.